Okay, so done one example of this now, but we've talked about how to come up with a transition matrix to convert some vector v in a vector space in which we have two bases, b and b prime, and then take that vector with its coordinate vector relative to b, multiply it by that transition matrix that we talked about how to come up with, and then what you end up with is the coordinate vector for v relative to the new basis b prime. Now you can do this kind of in a sequence of steps also. So just for example, if you have three bases for a vector space V, let's call them B, B prime, and B double prime. And if we pick some arbitrary vector V in our vector space V, we can multiply by a couple of transition matrices to get from one basis to the other. So here's what I mean by that. Let's suppose we are trying to convert the coordinate vector of v relative to b first to the basis b prime, and then take that vector and convert that to the basis b double prime. So kind of like two steps. Kind of working backwards from there. V relative to b double prime can be written this way. Notice the transition matrix here takes vectors from b prime and changes them into vectors relative to b double prime. So multiplying v relative to b prime by this transition matrix on the left gives me v relative to b double prime. But then this v relative to b prime can be found by taking v relative to b and multiplying it to this transition matrix, the one that takes b into b prime. So there's actually a product of two transition matrices happening here, one to get me to b prime and then the next to get me to b double prime. Because matrix multiplication is associative, I could regroup this and multiply this product by that vector. Notice what happens. This product takes vectors in b, takes them to b prime, which then takes them to b double prime. So this is actually the transition matrix. If I were to multiply these two transition matrices, this is the transition matrix that takes vectors in b into b double prime. So if we think about this for a second, using this idea of multiplying two transition matrices to get me a new transition matrix, if I have the transition matrix that takes vectors in b into b prime, and then the transition matrix that does this in reverse, takes vectors relative to b prime back into b again, then the net result of multiplying a coordinate vector relative to b by this matrix right here is that it returns me back to where I started from. So in other words, if I multiply a vector relative to b, it's going to take me into b prime, but then it takes me back into b, and the end result is exactly what I started with. I sort of summarized that here. So again, if I have a coordinate vector v relative to b, multiply it by this transition matrix, which takes me to one basis and then back to the original again, it's going to return me back to the exact same vector that I multiplied this by. However, there's something we can conclude with this, which is kind of useful, because if v is an n-dimensional vector space, then these coordinate vectors here they live in Rn. And literally every vector in Rn can be associated with a coordinate vector for this vector space. So this, I can alternatively write this way. For every vector in Rn, if I were to multiply on the left that vector x by this transition matrix, it returns me to x. That seems to indicate that this thing is behaving like an identity matrix, in the sense that we multiply x by that identity matrix and nothing changes. We still get that x back. There's a theorem that states that this would in fact have to be the identity matrix if this is true for every x, which it is. So we conclude from that this product is the identity, which means that these two transition matrices are inverses of each other. So again, the transition matrix that takes b into b prime is the inverse of the matrix that takes vectors relative to b prime into b. It kind of makes sense why that would be the case if you think about it. So That's pretty useful because we can now bring in any theorems that we have regarding invertible matrices into this discussion of transition matrices. Now, to kind of wrap up this section, I want to come up with a technique for computing these transition matrices. We've already talked about how to come up with a transition matrix for a change of basis like this. But in the particular case where we're working in Rn, if the underlying vector space is Rn, there's kind of a shortcut to that process. And it looks a lot like our inversion algorithm, the algorithm that we came up with for coming up with the inverse of a matrix that happens to be invertible. So what we do is we follow this step-by-step procedure. And again, the reason we can do this follows from the fact that these transition matrices are invertible. It's actually what makes this process possible. I'm not going to go through all the nitty-gritty of that. I do want to talk about how we use this process, though. So what we do is, if you want to come up with a transition matrix that takes you from an old basis into a new basis, then we create a partitioned matrix where on the left we use as columns the vectors that are in the new basis, and on the right we use as columns the vectors that are in the old basis. And then we row reduce this thing. We use Gauss-Jordan on this. Notice that, again, because these vectors because the transition matrices are invertible, when we reduce this, you are going to end up with the identity matrix on the left-hand side. The right-hand side will be your transition matrix. So, taking you from the old basis into the new basis, where again the old basis was on the right, new basis was on the left. And then as a final step, you just extract that transition matrix and say that's my answer. So let's take a look at an example where we want to do this. These are two different bases for R3 here. And we're not going to confirm that they're bases, but you can. These are relatively simple to show that they're bases. So if I want to come up with a transition matrix that takes me from B, this guy, into B prime, this guy, then I'm going to set up a partitioned matrix. And again, the new, you can't see that, the new basis we're going to put first. We're going to put that on the left. So in this case, I want to transition into the B prime basis. That's the new basis. These become columns. Read these from left to right, top to bottom. 0, 0, 1 in my first column. So 0, 0, 1, followed by 0, 1, 1. And then finally 1, 1, 1. I'm going to turn that a little bit. Okay. That's my new basis on the left. On the right, I'm going to put my old basis, the one I'm trying to transition from. So 1, 0, 0, 1, 1, 0, finally 1, 1, 1. Okay? Just like how we do matrix inverses. You know how to do Gauss-Jordan at this point. I'm going to write GJ there. That means Gauss-Jordan. And I'm going to skip the steps because it's not really worth the time to go through all that. You know what to do. On the left-hand side, we should end up with the identity matrix. And for this example, on the right-hand side, we're going to get this. 0, negative 1, 1, negative 1, 0, 1, and then 0, 0, 1. Okay? That matrix on the right-hand side, that's the transition matrix that I'm looking for. So I'm going to extract that and say P B into B prime is equal to 0, negative 1, 0, negative 1, 0, 0, and then 1, 1, 1. Okay? And again, that technique only works if the underlying vector space that we're using to change from one basis into another is one of the Euclidean spaces, that is Rn. We don't use this for other bases, but it's a nice technique. It saves you a little bit of time in those cases.